Okay, Math 1101. This is for first part of December. I believe it's December 1st. Don't have my calendar in front of me, but this will be the Tuesday after Thanksgiving, and we're into Chapter 6 quiz. And I thought it would be instructive to go through part of 6 because it'll be, probably the most important section on the final because we haven't had a chance to cover it before. So let's see what we can do. I'm going to work through all the problems here, and we'll see if we'll do the last scheduled class, the Thursday, which I believe is the 3rd, and we'll have some sort of live review at that point, and be sure to bring your questions. It's a good time for it. Okay, so number 1 says the goals scored by either team in games played by a soccer team are listed below according to the total number of goals scored in each game. We saw an example kind of like this before, and they'd like us to find the mean, median, and mode for this data. And so let's see what we can do with this. Let's do the mean first, means most important one. And notice we have 0 times 7 is 7, or 0, sorry. 1 times 14 is 14. 2 times 11 is 22. 3 times 12 is 36. 4 times 3 is 12. What I'm doing here is getting the total number of goals per column. And so, of course, in the 0 column, 0 goals. In the 1 column, 14 times 1. In the 2 column, 2 times 11. We just continue this progression out. And 7 times 2 is 14, and 2 times 8, that would be a high-scoring soccer game, 8 goals total. So we've got all those numbers there that have to be added up. And when you add them up, the sum is equal to 130. Now we have to find out how many total number of games there are. So that's 130 goals. How many games are there? Well, there's 7 plus 14 plus on and on. We find out there are 54 games. So 54 games. So I'll just circle it near the games part. So all we have to really take is 130 over 54. Let me see if I can scroll over and get a little more room here. Problem number 1, the mean is 130 over 54, which happens to be, as you already saw, 2.4. You can put more decimals in if you'd like. Now let's take a look at the median. The median I'm not going to hold you responsible for, but I guess since we have a little time, we'll take a look at it. The idea of getting a median is pretty important. 54 games that we're looking at, it would be cut in half at the 27th game and the 28th game. It would be right down the middle between the 27th and 28th. So if we can look for the median, between game number, pen keeps losing its strength. It doesn't want me to touch the screen. Okay, so I can't get a good read on this. I have to have bad handwriting. I wish I could figure this out better. 27 to 28. So let's just count the number of games as we go across. This is 7 games, and then 7 and 14 is 21. And 21 and 11 is the 32nd game. So that's how you do it if you needed to do this some other time. So that is at the 2 mark. So the median is 2, and they said it was 2. It's hard to read since I've been writing over it, but that's 2 for the median. Now the mode is very easy. You simply look for the most popular one. There it is, 14 games, although I obscured it a little bit. 1. So the most popular scoring game for both teams is 1 goal. Okay, so that's very good. Now, that's it for number 1. Let's take a look at number 2. 5-number summary, and I'm going to do this in thousands, so I'm going to use, like 27, 19.5. You could also try hundreds if you want. I'm just going to drop all those extra zeros, and I think the nearest thousand seems to be a very typical way to go. So we want to get the 5-number summary, but in order to do that, we have to put the numbers in order. So I'm going to get a little room and do that. It's tough to show the picture of the problem and the scratch work at the same time. So when we sort the numbers, what happens is 17,000, I wish you could see it, is the lowest number. 18 is the next lowest. 19.5, one we just pointed out, is next lowest. Let's take another look. There it is, 19.5. There's 24.5, etc. Well, what's the next one? After 19.5, looks like we'd have 24.5, the one I just wrote down. So let's continue and keep that up. Hopefully you worked on this before you're looking at this. This would be the best way to go. Although the answers are staring right at you, the answers are not always what we're looking for. We want to see the work as well. So, just spouting out answers without really knowing what they mean is not really learning anything. 25.6 is the next one, so I'll go ahead and put that down. We also have a 27, a 27.8, 29, a 30.2. This is 27.8. Okay, and 32.7. Okay, how many values are there? There are 10 values, so we'd cut the data in half. Okay, so we have to average these two numbers. 25.6 plus 27. We have an even number of data points, so that means we'll have to average the two middle ones. This is equal to 52.6. Of course, we'll have to divide this by 2, which gives us 26.3. That's the median, or Q2, if you want to call it Q2, we'll take that. And then remember, we never include the median. Never include the median when you were to find the Q1, Q3, and all that. But let's go ahead and take care of the minimum. That's pretty easy, the 17, the maximum, the 32.7, in terms of thousands, of course. Those are very easy to do in the median. And you should only do Q1 and Q3 afterwards. So let's see, 25.6. Yeah, we've got 5 values on each side. So yeah, we do have one central number. And that number out of the group of 5 is Q1. And then we look at the last group of 5, and the 29 stands out as being the third of 5, so that would be Q3. And mostly people have been getting this right on tests, so that's certainly good news. Okay, then let's take a look at the numbers in 17, 19.5. Let me write them again. It's always good to focus on them. A few people have decided not to really tell me what they are and just sort of walk around it a little bit. So 25.6, of course we said 29, 32.7. If you put the numbers in order, that's considered to be obviously the 5-number summary. If you put them out of order, then you better tell me what you're doing. I'd prefer you do them in order. Okay, anyway, we do see the numbers, and they match just in terms of thousands. Now we have number 3, calculate the mean and standard deviation. So this one, I don't think I'm going to do the whole thing. You'd probably kill me if I did. So let's take a look at the mean. We sum all the numbers up, and so we see we have exactly the same data set, and when you sum them up, you get 251.3 thousand. So this time, I guess I'm just going to write the thousands down. So these were in thousands here. This one's not. This is just the basic sum, 251,300. Of course, we'll divide that by 10 to get to the mean, because there are 10 data points. And dividing by 10 is about the easiest thing in the world. Just move the decimal over, 25130. So 25,130 is the central value according to the mean. Well, let's take a look at the standard deviation. Now, I gave you an example with another ERA calculation, and you could certainly take that to heart in the prior lesson. But this one has much bigger numbers, unfortunately, and I didn't think to move the decimal over, and even if I had, I would have had a lot of decimal points. So the main thing is to take each value and subtract it. Let me just do the first couple of values. And, of course, you have your value x minus the mean. And so for value number 1, in order, 27,000, we'll subtract away the mean, 25,130. Okay, that's going to be what we call the deviation. We'll just say DEV for short. When you subtract them out, you do get that's 27,000. You get a positive 1,870. But then the squared deviation, that gets to be kind of unsightly, shall we say. That one happens to be 3,496,000. and 900. So that's a lot, and we continue doing that for a while. No, I'm not going to hold you responsible for this. Let's just do one more, show you where we're headed. 19,500 minus 25,130. There is another formula, by the way, but since most people use technology, that formula has kind of gone by the wayside. It actually did take a lot less time, but it didn't really show you what was going on. So here, at least we have the advantage of showing you what's going on. We're seeing how far each point is away from the mean. And then we square it, kind of like the distance formula or even Pythagorean theorem, and we collect them all, and then we square root them just to put them back on the same wavelength. And that would be our unit of measurement as far as the variation would be, and that's the standard deviation, as we're trying to say. Well, with this number here, this is actually pretty far off, one of the further ones that's away, and it's off by minus 5,630. Of course, as when we square the numbers, all the numbers get to be 0 or positive, and this one is, this is what I'm talking about, 31,696,900. And I spent some time working on this, and for various reasons, every single number ended in a 900. There's number theory for that, but I'm not going to go into detail on that. So anyway, ... and we go ahead and sum them up. And as we go through the broad strokes, even though with unsightly numbers, the sum is equal to a whopping 257,861 million. So 257 million, I should say. Divide by 10, because you have to divide by n, and that's relatively easy. That's 25,786,100. And then we square root it. And when you square root it, you're down to about 5,078. So there in broad strokes, without all the grisly details, is your standard deviation for problem number 3. But notice I put a few dots in there. So if you're feeling ambitious, go ahead and finish that one off for me. And no, I will not ask you for anything that large on the test. And same with the ERAs, those have decimals. Most decimals I would ever give you are tenths, and I'm leaning strongly to thinking maybe just whole numbers will be fine, and certainly a lot smaller than these. So I'll kind of hit a balance. If you can do the ERA problem and get started on this one, you should have little trouble with it. Now, for various reasons, I think switching number 5 and number 4 make a lot of sense. 4 grows out of 5. They just got these kind of mixed up a little bit. Okay, so let's go to number 5, ahead of number 4. The weights of oranges in a harvest are normally distributed. That's the bell curve. And with mean weight of 150, standard deviation of 10, calculate the z-score for an orange weighing 160 grams. So we saw the English version of this, and if you recall, z, I'll just put it up here, is equal to the value minus the mean, however you express it, over the standard deviation. I'll just say SD for short. And that means that Z for part A will equal the value 160 minus 150. That's divided by the 10. And amazingly, we get 10 over 10, which is exactly equal to 1, 1.0. They didn't ask us for any probabilities. It's just 1.0. We can use this in problem 4. Here in the part B, we have the value changes to 135. And now I'm going to just divide that by 10. We do get a minus 15 over 10, which does give us a minus 1.5. So our z values are 1.0 and minus 1.5. In fact, you can see the answers right there, so no hiding the answers. Well, now that we've got 5 out of the way, let's go back and do number 4 and see what's going on. I can squeeze it in here a little bit. Well, there we go. Let's try it that way. Okay, the weights of oranges in a harvest are once again normally distributed, same 150 grams for the mean and standard deviation of 10. And we have a supply of 1,000, which turns out to not really affect the problem in this particular case. But, and sometimes it does, but not in this particular case. You're not into that kind of stuff yet. In fact, we're not going to get there. How many will weigh between 140 and 160, and how many will weigh between 130 and 170? So I've always been fond of a picture, and I would just be thrilled if you gave me one. But let's just go ahead and put down the values that we're interested in, 140 to 160. And of course, our mean is right down the middle. I don't have room to cram the 150 in. But I'm trying to shade in this area here. That's what I'm trying to find out. So this is where we get our z's. And in fact, we've got one of the z's already. So let's go get the other z. Z for the 140 would equal 140 minus the 150, the mean, over 10, which is minus 1. And we just found out that the 160 was a z of plus 1. In fact, if you forgot already, it's right here, 5a. So they got us to do part of it. So now we can use our table. The table will be given to you. You will not have to worry about it. And so what we'll want to do is to try to find the probability. So I'm going to convert these to decimals. I don't have the table punched up here, but if you look at the 160 for the z equals 1, that puts us in the 84th percentile. In other words, in terms of a decimal that you can use on your calculator, it's 8413. That's the 84th percentile. I'll just say that. I'll abbreviate percentile as percentile. And z equals minus 1 puts us in a much lower percentile. That's about the 16th percentile. I'll just go ahead and say 0.1587. And what that means is we can subtract these probabilities. So in other words, I think this cuts off. Yeah, it cuts off. But the 160 has 84% going in back of us, and the 140 has only 15 or 16% going in back of us. So when you subtract those two numbers, you'll get the middle 0.6826, and that is actually one of the empirical rule type of conditions that we may see. But let's go ahead and look at, as we just did A, let's look at 4B. And it's pretty much the same idea. Between 130 and 170, we can take a look, and same graph, really. It's just stretched out a little bit further. 130, 170, and our mean is down the middle. And yes, we're doing the same. Find what's happening in between. So we're going to need to get the z's. So let's start with the first one. Z for the first one is the value 130. Subtract away the mean 150. Divide by 10. Nice round numbers. This doesn't usually happen. So we get minus 20 over 10. That is a minus 2, minus 2.0. And the other z is 170 minus 150 over 10. And that's positive 20 over 10, which is a plus 2.0. So this illustrates an even more important part of the empirical rule. For z equals 2, well, first of all, I'll start with a positive 2. It's good to go with the larger number minus the smaller number. So we'll find out what these values are and subtract them to find the area in between. So for z equals positive 2, the probability from the table, and of course we're using the table for probability, or you can put this in percentages. Just multiply by 100, don't forget to do that. So if we have z equals 2, that gives us the 97.73 percentile, almost the 98th percentile, but we're using 4 decimals because the table does give it to us. And then we have z equals minus 2, so this is much more stretched out, and that gives us only the bottom 2%, 0.0228. We subtract those, we find pretty much the 95% in the middle, 0.9545, or simply 95.5%. That would be fine too. So that's what we found, and this is much more likely than the other one. If I can get this to go back on. And here we had the middle 68%. This is plus or minus 1 standard deviation. This is plus or minus 2 standard deviations, where we find a big chunk of it, over 95% of it, is in that zone. Okay, let's see here. We have number 6 that we could try. And some of these problems are much faster, by the way. So this will go a little quicker here at the end, I'm afraid. For a certain disease, 40% of untreated patients can be expected to improve within a week. We observe a population of 80 untreated patients and record the percentage who improve within 1 week. No medicine involved. Or perhaps there is, they're just not saying. but it's all the same condition, whatever it is. Whatever it is, these people are all being treated the same, or untreated patients, I guess. And so according to the central limit theorem that we did talk about, these percentages are approximately normally distributed under most conditions, and we can find the mean and standard deviation of this normal distribution, and we could round the standard deviation, and we found that various things occur. They did say the 40% was given, so that is the mean. There's nothing to calculate. I don't know if I would waste your time with a question like that, because all you have to do is copy down the answer. 0.40 would also work, by the way. Now let's see how they got this formula going, since we have it written down in the answer. Let's go ahead and take a look at the formula. So for number 6, we're looking at the standard deviation, sometimes called sigma or SD, whatever one. I'll take either one. And the formula we had, in terms of percentages, now this is already inflated up to percentages. This book does this. So if you like working with decimals, so do I. You just have to remember these answers are in percentages. P times 100 minus P is divided by N. So that gives us, in terms of percent, here P would equal 40, not 0.4. So that does take a little bit of remembrance. And 100 minus P is 100 minus 40. And we'll divide that by N, and N was 80. There's 80. And we'll square root it. So let's put another step in. I guess we've got 40 times 60 over 80. Cancel some 10s. You get 240 over 8. By now, you'd probably use your calculator. I'm just saying this happens to be exactly the square root of 30. It's kind of a weird coincidence. But that turns into 5.48. And that is already in percent. 5.5 would be fine as well. But, they did say 2 decimal places. So, okay, I guess we don't want to stop there. Those rare cases where they tell you what to do, please do it. Otherwise, I have to ding you a point. I don't want to, but I'd have to. So I almost forgot, 2 decimal places. So that's the standard deviation. Mean of 40%, since we're talking percentages, standard deviation will be 5.48%. And then you could start adding 1 standard deviation each side of the mean, or 2 standard deviations from each side of the mean. And then notice you've got, 68% within 1 standard deviation, and 95% within 2 standard deviations, that kind of thing, which is standard for a normal curve distribution. Okay, so number 7 builds on number 6, and this time they're going to ask us the following. Use the mean and the standard deviation calculated in the preceding exercise to find the percentage of test groups of 80 untreated patients. And it turns out we're not actually using that number, but that's okay, in which 50% or less improve within a week. Round your answer as a percentage to 1 decimal place. Okay, so 7. Let's see if I can go down here a little bit. Get this going. Okay, here's number 7. And number 7 had, and I like the sketches. This isn't a real formal statistics class, but if you want to explain what you're doing to me, a sketch is really nice. This is assuming I even have PDFs on the final. I'm toying with the idea of not even having PDFs on the final, but I haven't come up to a decision on that yet. We're kind of on our own. We've only had like 1 meeting all semester, and PDFs certainly let me see what you're thinking a lot better, and it does help me with things that cannot be typed into Blackboard, although some of you do a very good job of typing answers into Blackboard. But I don't think you can type a normal curve into Blackboard very well. So anyway, I'll come up with something. If I don't, we'll work out something else for a PDF, but I may go for the PDF as I've been doing. Okay, so we do have in percentages an average of 40%. We did establish that as the mean. But now we're interested in 50% as a new cutoff, and everything that's less than that. So we're headed this way. So let me lightly shade that area in. Anything less than 50% is what we're interested in. Okay, so let's find out what Z would be. Z, once again, would be the value minus the mean over the standard deviation. The value we have is 50. It's in percent, so just leave it alone. The mean was 40. And then we divide by the standard deviation, which is not 10 this time. It's that new number we found back here, 5.48%. So let's go ahead and put in 5.48. And that's what they have in their answer. They set up part of it for you, which is kind of them to do that. And as you divide, 10 divided by, of course this is 10, over 5.48, that gets us a z to one decimal place of 1.8. So many steps here. This is a fundamental problem in a statistics class. So believe me, I'm very tempted to give you one of these. Sorry, I seem to be losing my voice right at the moment. Apologize for that. Anyway, we look at the table, and since we're going to the percentile, this is perfect for a percentile because percentile is a cumulative measurement that stops just shy of the number. So the percentile is the actual answer. Is the answer because it's left facing, it's a cumulative number, it's a less than problem. So percentile, it's hard to read, I know. And so we look it up and we see 96.4%. I rounded that one. I'll just convert that to percent and you'll see the answer is about 0.964. So 96.4% of the time this will occur. And so what's the chance at which 50% or less improve? That is, as many as 50% will improve, very high percent. There's only going to be about 3% of the time where you get even better and rosier results. So this is 3.6 if you subtracted that from 100. We didn't ask that question. I just thought I'd do a follow-up. So for it to be extremely good, like above half, a majority of them getting better on their own, we only expect 40. That only happened almost 4% of the time. And yes, we can actually quantify this stuff. This is how people make decisions based on these business models. And whether they're positive or negative, I guess depends on whether it's involved in advertising or not. Well, anyway, okay, let's see. They've got number 8 down here. Let's get started on 8, and I'll continue this on another page. Explain the meaning of a poll, and some of these are quite easy. It says that 55% of Americans approve of the job the president is doing, with a margin of error of 3% and a confidence level of 95%. Well, that's the go-to standard. So really, all we have to do is say 55 plus or minus 3. So as we subtract 3, we get 52. Of course, that's percent. As we add 3, this is about as simple as it gets. I hope everybody gets this one right. And you get 58%, and that is your interval. That's called a confidence interval. But it's a 95% confidence level, which means we're going to be right all but 5% of the time. And so they say in 95% of such polls, the reported approval of the president will be within 3 percentage points of the true. And we can continue. Of course, I've already got the answer there, 52 to 58%. Let's scroll down and get to page 2. We can see a little bit more information. Yeah, so that's it. Just add and subtract 3. Talk about a piece of cake. That's really simple. And I don't say that very often, but this is certainly one of those. A poll asked for number 9, 800 people, their choice for mayor. What is the approximate margin of error for a 95% confidence level? Well, we have a formula that you should know, and since you do get a page of notes, you could go ahead and put this in your notes. Let me see if I can squeeze this in here. I'm not sure if I can cross the line. No, it doesn't go below the line. So let me see if I hit the pen and just go to number 9. Here's number 9. Okay, good. Now we have the formula that we referred to, and it'll say that the margin of error, that's supposed to be a 9. I'll just say ME, not me, but margin of error, is equal to 100 over square root of n percent. This is n, but n, they just said was 800. And yes, this is for the 95% confidence interval. Do not worry about that. That's the only one I plan to ask you. I don't think WebAssign goes outside of that, but if they give you something else on a homework problem, just go with it. They could have a slightly different formula. I know they used to do that. Maybe they still do. If they give you like 90 over square root of n, just go with that. But I'm not going to give you anything but 95% on the test. So that's nothing to really be concerned about. So n is 800. So that means, continuing our train of thought, we have 100 over the square root of 800. And of course, that's percent, so I should keep that in mind. Well, the square root of 800 is 28.3. That's rounded. And yes, I kept all the decimals in my calculator, just in case of round off error. And in a stats class, I do get very picky about it. Here, I probably won't be as picky, but still, be careful. I've been trimming trees all afternoon, so I have a little bit of congestion with the dust and stuff like that. We need rain. Anyway, 3.5%. So yes, the number is in percent, so I should probably keep reminding you of that. And this isn't one of those problems where you have to convert to percent. It's already done in percent. The formula is a percentage type formula. Now, what about number 10? This is just the reverse. These formulas are really the same. What sample size is needed to give a margin of error of 2.5% with a 95% confidence level? So yeah, kind of shelved that. The only real number they gave us was a margin of error of 25. So you could try to cram it into that formula, but if you make a mistake doing that, I'm going to kind of notice, because we do have a specially tuned formula just for this. Remember, sample size is n, so I'm just going to use that. That's the most important variable in all of statistics. And if you take a full-on statistics class sometime, they use n in virtually every section. It's hard to find a section that doesn't have the sample size involved. Okay, this formula, though, as you probably remember, is 100 over m. And to give equal time, let's go ahead and say that me is also equal to m. And that will be squared. Why it won't work, I don't know. Try my other pen, see if it's going to be any better. Let's see, it's good to get some, yeah, there we go, and we'll have to square that. Okay, so now m is equal to 2.5%. Now this is a percentage formula. I don't think they crammed it into the formula, but that's meant to be 2.5. This is almost a contradiction in math circles, but this book has been, quote, dumbed down for you. And I think it will help most of you, but it will distract some of you who've already worked a lot with decimals, maybe had some more advanced math or something along those lines. But the point is, don't overthink it. Just put the 2.5% in just as 2.5. Now, when you divide 100 by 2.5, you do get 40, and 40 squared happens to be 1,600. That is a minimum sample size, by the way. So that would be sample size is needed or necessary. So this is also known as a minimum sample size. In other words, we'll always take more. But at 1599, we don't have quite the accuracy we're advertising. And, these are approximate formulas, so I really shouldn't say that. We do have actually better tools in a full-on class. So if the book actually showed one that had 2,415 versus 2,500. And so, yeah, the poll got away with it because they knew the exact formula, and we're not quite doing that here. We're kind of simplifying it just so you can get an overview of statistics. We're not trying to teach you 15 weeks of statistics in 3 or 4 weeks. Seems like we are, but we're not. Okay, let's look at just a couple more. We're getting close to the end. Number 11, for each of these situations, determine whether the results described appear to be statistically significant. So this is one where you don't really have to show a ton of work. But you're walking down the street and encounter 3 people in a row with blonde hair. Now, I don't know what the blonde percentages are. That would be a little unusual, but it would not seem to be a big deal. Now, 3 redheads in a row, that might be a big deal. Or 3 people who have dyed their hair blue in a row, that might be a big deal. But, blonde or brown hair, that'd be particularly easy. Lots of people have brown hair. So that would be a big no. However, part B, you cut a deck of playing cards 30 times. You draw a card, and you get an ace every time. Wow, that would be kind of hard to do. And I'm going to say big yes on that one. If you want the details, there are 4 aces out of 52 cards. This is something you do not have to worry about. I just thought I'd quickly explain it for those who might be interested. 4 out of 52 is 1/13. So 1/13, about 7% of the time. That would have to be raised to the 30th power. And so it's not too hard to show that this would be around 4 times 10 to the minus 34th power. In other words, you got like 34 zeros after the decimal point. Okay, that's rare. wouldn't wait around for that one. So if it actually happened, you'd have to say with just about 100% certainty, as close to 100 as you can get, that you got it in a magic shop or somehow got 52 other card decks and got them all arranged, or maybe just less, but you'd have to get a bunch of other cards and take only the aces out. That would be very weird. I can't imagine anybody doing that. Okay, let's go back and take a look at a couple more. And here is number 12. A clinical trial for an experimental drug finds the drug is effective with a p-value of 0.08. Explain the meaning of the p-value in this case. Would this result normally be accepted as statistically significant? So a p-value, and the book does a very good job of explaining it. Some books botch it up with a bunch of theory and garbage, but here your book just gets to the point. The outcome of this clinical trial, whatever it may be, and that is effective, and it would occur by itself, by chance alone, if the drug had no effect 8% of the time. Okay, that's all right, nothing wrong with that, but it's not usually considered to be a big deal, statistically significant, rare enough, because the p-value is larger than 0.05. That is, 0.08 is simply greater than 0.05. We're trying to get it to happen less than 1 in 20 on its own, and here we've got it happening 8 in 100 times on its own. Still kind of rare. I'll just throw in some extra information you don't have to worry about. But what if you had a cutoff of 0.10? It does actually happen. They just didn't advertise it. And if that was the case, then you would have 0.08 is actually less than 0.10, and that would be considered to be statistically significant. If our criteria, called alpha, by the way, is 0.10. That's a what-if situation. So I just couldn't help but throw that at you, because sometimes 0.10 is used. Not much, but it could be. Also, decide whether the following variables are positively correlated. Do they go together? Are they negatively correlated? Do they kind of go against each other, or just have little or no effect, no real effect on each other? So your grades and the number of hours a week you study. We'd like to see them perfectly correlated, but unfortunately that's not going to happen. Some people, I remember knocking my head against the wall and studying 13 hours a day for this one math class that, wow, well, I got a D, and another guy had straight A's. He got a D. That was an impossible situation. Oh, the dean was teaching it, so we couldn't complain to anyone. But that's another story for another day. But normally speaking, your grades, the number of hours a week you study, are somewhat correlated and positively. Let me just put a big plus sign there. So positively is the plus sign. Negatively correlated is the minus sign. And uncorrelated, I'll call that a 0. How about letter B, your grades and the number of hours a week you party? Well, especially if the hours a week become like more than just 1 or 2, then you'd have to say that it quickly heads downhill, at least in most cases. And I lived in the dorms of Cal Poly Pomona, and yeah, I was lucky enough to be in an older dorm. We were all 25, oh my goodness, and we saved our partying for Saturday night. We didn't party every night like some of the other dorms did. Plus, I used to wake up early and study, so I could actually get studying in for all the music started hitting. But anyway, another story. Let's go to part C. Your grades and the number of cookies per week you eat. Now, I guess if you ate hundreds of cookies per week, you'd probably get pretty obese, and maybe it would just not work out for you. But in most cases, the cookies have little to do with it. Oh, perhaps the sugar rush would get you working kind of like a cup of coffee or something. There may be some minor effects, but I think if you really quantified it, you wouldn't see very much to choose from. Might be one of those where you get a 0.02, where it's very slightly correlated, nothing significant. Okay, the daily average temperature in the sales of cell phones. Well, we've seen where temperatures might affect, the weather, and people go swimming and then they get bit by sharks, and so, one could, talk about a third variable somewhere in there, but I don't see any real change here. I don't think cell phones, they're so popular, it doesn't matter if it's cold or hot. There doesn't seem to be very much correlation. That would be interesting to find out. But they tell us it's 0, so I have to think it's pretty close to 0. Does it go up in the winter when people have less to do? Maybe. I don't know, especially back east. But around here, the weather is moderate most of the year. Okay, here's another one, daily average temperature in sales of overcoats. Okay, as the temperature goes up, so this one almost had me fooled, sales of overcoats go down. and vice versa. When the temperature goes down, the overcoats go up, and that's what we really think about. So when the temperature drops, the overcoat sales go up. So that's a negative correlation. That's a negative one. So yeah, if you're looking at temperatures, it going from colder to hotter, and sales would go from better to worse in the same progression. And then I think one a little bit easier to see, the daily average temperature goes up, and the sales of shorts, they go up because it's getting hotter and people don't want to wear long pants. I went all summer long and most of the fall without even putting long pants on, but things are changing now. Okay, so that will pretty much do it for a quiz here. I've got a lot more to say and some problems I'd like to work out during the live lecture too. But during the live lectures on Tuesday the 1st, please bring problems that you may have. That's always a good time to do them so everybody can see them, and I'll get the whiteboard going and we'll see if we can work out some problems. Or if you just want to send me them by email, that will work too, and I can work them out during the live lecture. Of course, it is a cumulative final, and you'll have until just before the final starts to finish your WebAssign work. But I hope that you've been working on it the whole time and you're not rushing to get them all done. You do get the advantage of several opportunities to work on your WebAssign, so that part's pretty good. But like with my other class, the 1201, they only get one shot. First shot counts. Oh, they can do more, but it doesn't count. So that's kind of weird. I believe you guys get about 5 attempts each time, as I remember. That was pretty much what they gave us. I didn't change it. So please work on the WebAssign and work on some other problems. I've always suggested working on odd number problems that have answers in the back. These quizzes are a little bit stark in that they have the answer right in front of you, which is not my favorite way to do it, but at least it does give me a platform to get through practically all of Chapter 6 that matters. I can't think of anything I might have missed. So, of course, we'll cover a little bit of 1, a little bit of 3, a little bit of Excel, and 4, 8, and 6. So all that will have its place on the final. I know I'm not going to double the final problems. That doesn't make any sense. But there will be more than the last midterm. Yes, it was a 75-minute test. Let me write this down. 75-minute test for the midterm, and there's going to be 120 minutes for the final. And that's actually an increase. So we had 110 minutes all these years. We only had an hour 50, which is 110 minutes. And now suddenly it's a full 2 hours. So whenever your final starts, you get a full 2 hours until it's done. So even though the class is only an hour 15, you have to get to work. Please notice that we'll go for full 2 hours. It depends on what section you're in, so you just have to check that out, and I'll have more information on that coming up. It's in the syllabus too, by the way, and there will not be any changing of the dates on the final because that's cast in stone. That's something the university does. The tests, we get to change a little bit if we need to. I didn't want to, but things are so new now that I did have a few changes, but try to let everybody know well in advance, but no changes for the final. Please be here. Please make sure your Zoom camera works. That's another important thing. One of the 1101s, I won't say which, had a large number of people without their Zoom cameras on, and I cannot grade your tests. So if you want to make sure your final is graded, please have your Zoom camera on, and I need to see your face. If you're just a silhouette, all I see is your left ear or your nose, that doesn't count. You'll have to check the chat box. I'll make sure this is all in the instructions and in the email, that you have to be visible. If I can't see you, we have to assume you're cheating. That's departmental policy, and I happen to agree with that. And yes, there are more cheaters now than there used to be. I know most of you are not, thank goodness, but there is some around it, and we don't want to reward cheaters. I'd like to send them all to jail myself, but that's just me. Halfway kidding. But anyway, no cheating, please. And yeah, we'll have more to say about the final and the live meeting, and it'll be coming up very soon, the Tuesday and Thursday of finals week. So I think that'll do it for now. I do have office hours during the final week, and I'm speaking a couple of days before Thanksgiving, but you will have seen this. There'll still be one day of finals. Final office hours is what I'm trying to say, but I do not plan to have office hours during finals week. That's not usually a standard deal, and we've got other changes in schedules, and so it becomes a little tougher to do that. But we'll still have plenty of time there, and there's always email, so please send me emails if you have questions. And best of luck, and I think that'll probably do it for now, and we'll talk to you soon. And we'll be live on the 3rd of December, which is a Thursday. I believe that's December 3rd. Okay, we'll talk to you later. Bye-bye.